My final report focused on understanding if I could model the effects of changing the length-to-diameter ratio, or L/D ratio, of a simple submarine hull shape. As you would expect by its name, the length-to-diameter ratio of a submarine is the ratio of the fore-aft length of the submarine to the hull diameter. The L/D ratio strongly correlates with the overall flow resistance of the submarine, which relates to the maximum submerged speed of the vessel. Thus, the L/D ratio is a metric used during early stages of design to determine what impacts the ship's speed and mission capabilities may occur if the hull diameter or length of the ship is modified for other reasons. The chart on the slide illustrates the effects of changing the L/D ratio. Generally, the L/D ratio is determined by two factors: the drag caused by the pressure drop over the length of the hull, or pressure drag, and the drag caused by frictional resistance of the hull, or skin friction. As shown in the chart, the theoretical optimal L/D ratio occurs somewhere close to 7. The objective of this report was to attempt to recreate the above chart by changing the dimensions of a simple submarine hull shape. To get into my methodology, I first needed to decide what kind of submarine shape I was going to study. I opted for simplicity, so I decided to study a bare hull without any control surfaces. To model the hull, I decided to use a hemisphere for the nose, a cylinder for the body, and a cone for the tail end of the sub. Using this basis, I varied the hull diameter to generate 10 submarines with various L/D ratios, as shown on the table on the slide. I kept the volume of each submarine constant to eliminate that variable. Once the dimensions were decided, I generated 10 SOLIDWORKS models. This portion of my report largely echoed the airfoil gouge that Dr. Hobson provided at the beginning of the term. Each SOLIDWORKS model was a two-dimensional cross-section of the three-dimensional submarine. I created a sketch for each submarine as shown in the top right corner. Following, I extruded a rectangle around each submarine and cut the hull shape out, as shown in the bottom right image. After I finished the SOLIDWORKS models, I created an ANSYS workbench for each of the models. I simulated 10-knot water flowing in the x direction for each model. After running a solution, I calculated the global force in the x direction on the wall of the submarine, similar to what was directed in the airfoil gouge. The plot in the top right displays the L/D results I generated the first time around. Clearly, these were not the results I was looking for, since there was no clear minimum nor a clear trend. Following conversation with Dr. Hobson, I decided to change two aspects of my model. First, I dropped the floor of my solution to 1 × 10⁻⁸ rather than 1 × 10⁻⁵, as I had preliminarily set the solver. Additionally, I updated the mesh for each model to create a much finer mesh around the submarine. It may be difficult to see, but the image on the left shows the revised mesh for one of the models. The mesh is relatively large until you get to the wall of the submarine, where the size of the elements drops off significantly. The two images on the right show the effects of refining the mesh near the wall of the submarine. The top right image was the solution generated by the original meshing scheme, where the elements close to the wall of the submarine were relatively large. The bottom right shows the solution of the revised mesh. In particular, note the refinement of the revised solution closer to the wall of the submarine. Using the revised model, the chart on this slide was generated. The most obvious takeaway from these results is that there are both a clear trend and a local minimum at an L/D ratio between 7 and 8, which is what the theory predicts. However, the results also become less reliable at lower L/D ratios, which I cannot explain at this time. Overall, however, this was a step in the right direction. At the very least, these results showed that the L/D ratio could be trended using simple geometries in ANSYS. In the end, I ran out of time in this term to fully squeeze the potential out of this project. To continue this study beyond the simplicity of what this report considered, I would do the following. First, I would calculate the skin friction and pressure drag to see if the trends match the theory described at the beginning of this presentation. Next, I would change the submarine shapes to reflect a more realistic shape. For example, you could change the bow from a hemisphere to an ellipsoid. You could smooth off the transitions between each of the sections. At the aft end, you could round the point off or make a more representative shape of the propulsor. You can change the size of the submarine to be more prototypical of an actual submarine. The scale I used was about 1/10 of the actual size of a submarine. You could include control surfaces such as the sail, fairwater, and stern planes, or dihedrals to see how that affects the L/D ratio. And lastly, you could change the speed of the fluid flow to see if that changes the L/D ratio behavior.